Hi, in this video I want to talk about various kinds of applications that we can put piezoelectric materials to. Okay, let's start by just re-looking at the slide that we had already looked before. And remember what we said here? We said that if you have a solid material, okay, and you apply a force on it, it usually strains, right? And if you apply an electric field across a dielectric material or a solid material, you get some displacement current in it. But in a piezoelectric material, a force results in a charge or a voltage appearing in the faces of the crystal. And if you apply an electric field, you get a stress or a strain. Okay, so let's start from there. And the two equations that kind of define these are these two equations as we looked before. So let's start from there and look at some applications. Okay, so in the first application, what I want you to imagine is that T is 0. That is, we don't apply any stress to the piezoelectric material. All we do is we apply a constant voltage across the crystal. If we do that, what's going to happen? Now these are our equations, and you set t equal to 0. We see that there is going to be a displacement current or a charge that will develop across the crystal. But what is more interesting is looking at this stress strain relationship here. If we set t equal to 0, what we get is there is still a strain, and that strain is dependent on the electric field across this crystal, right? E. And E is dependent on the voltage that we apply. To be more precise, it's going to be V divided by H, where H is the height or the how wide the solid material is. So what is strain given by? It's given by delta L by L, and as I said, electric field is given by V by H. So what we get is we get a strain that is proportional to the voltage that we apply. So in a crystal, if we do not apply any stress to it, that is, if we don't apply any force, we just leave it free to move, and we apply a certain voltage on the crystal, what is going to happen? The crystal is going to deform up and down. And therefore, we can use this piezoelectric crystal for micro positioning. We can control the position of a particular object by just applying different voltages to it, right? So that's the first application of piezoelectric material that I wanted to talk about. Okay, let's look at the second application. So in this case, what we do is we assume that the electric field is 0. How do we make the electric field across a crystal 0? We make it by shorting the two terminals of the piezoelectric crystal, two faces of the piezoelectric crystal. And we don't allow any charge to develop across the two faces of the electric crystal. So because we have shorted this, there will not be any negative and positive charges that develop here. Okay. Now in this case, what is going to happen? Take a look. This E is going to be 0. This E is going to be 0. Okay. And now if this E is 0 and we apply a force on this crystal, that is, we apply a stress on this crystal, there's going to be some strain. That is as usual in any material. But look at what is interesting. If you apply a stress on a material, what is going to happen? Because of this equation, you will get a displacement current which is equal to d times t, and this displacement, this d, can be written as d times L into W. So the charge is written as d times L into W. So the displacement current is basically uh, uh, the charge per unit area in this case. Okay, and that is equal to d times t. So therefore, your charge is proportional to the force that you apply. So when you are applying a force on the crystal and you just put a short circuit here And if you can measure this current, this charge that is flowing here, that gives you uh, an estimation of the force that is being applied in the crystal. And this is the way we can use piezoelectric crystals to measure vibration, force, pressure, or deformation, right? Is that all right? So that's the second application. Let's look at another application. Let's look at what happens when you make the strain equal to zero. How do we make the strain zero? We make the strain zero by giving so we apply a force, right, to a solid, and because of the force, the crystal should strain, should deform. But we prevent that deformation by giving a voltage so that it counters the strain because of this force. Okay, and in that case we can actually calculate the charge that will develop across this piezoelectric crystal, and we can see that charge is going to be proportional to the voltage that is being applied and the different constants here. Okay, uh, let's move on and look at one more application. Let's say we make sure that D equal to 0. That is, the displacement current here is equal to 0. How do we ensure that? We just open circuit our circuit. So we just leave the crystal as it is. Okay? So what happens then? If we leave that, as you apply force on a particular crystal, what you would find is you will get a strain on the crystal, but the strain is not the same strain as you would get in a normal solid material, right? It's not going to be proportional to the force or to the stress, but it's going to be reduced by the permittivity of the medium, by this quantity. So your compliance of the material is reducing by this quantity. Okay. So in most piezoelectric materials, what we do is we are basically using, I'm going 2 slides before, we are basically going to be using this uh, mode, in which what we are doing is we are measuring the current or the charge that is developing across the crystal as a response to the force. So this is measurement, and the application before that is where you can have micro positioning. So here you can use the piezoelectric crystal as an actuator, right? So piezoelectric material can both be used as an actuator and a sensor.